Hello, everyone. Today we're talking about DomiKnowS, a library for integration of symbolic domain knowledge in deep learning. I am Parisa Korjamshidi, faculty member at Michigan State University Computer Science Department. I will be presenting this work with my PhD student, Hossein Rajabi Faqihi. The motivation is that deep learning models nowadays are data hungry, and we need large amounts of annotated data, which is expensive. But the idea is that directly encoding domain knowledge into deep learning models can reduce the need for large amounts of data. However, domain knowledge is often expressed symbolically, but that is an advantage because this will provide better interpretability to the models. There is a challenge, however, here, and that's the large gap between the current tools that provide deep learning design, like designing deep learning models, and the tools that provide symbolic reasoning capabilities. That is why implementing algorithms that integrate the two capabilities is challenging. DomiKnowS is a library which its backbone is just deep learning libraries like PyTorch here. And it introduces a new interface and symbolic representation via which we name architectures. And then we can express logical expressions, first order logical expressions using these named concepts. And then these logical expressions can be used as hard or soft constraints on the output concepts of the deep models based on variety of algorithms. Here is an example to show why this is helpful. For example, we have entity mention relation extraction task. Given a sentence like Washington covers Seattle for Associated Press, we are going to classify what are the entities and types and the relationships. The independent models might decide that Washington is a location, and the Associated Press and organization relationship is work for. However, our domain knowledge between concepts says location cannot work for organization. So the model based on this domain knowledge, if it's used as a kind of constraint, will change its mind and decide that Washington is a people. So we are maximizing this global objective subject to these constraints. If you want to use DomiKnowS library, your program will have three main components. The first component is defining and declaring your data, because we are dealing with a structure. We have a generic graph-based data modeling, and then you're going to use the first order logical expressions to express the relationship between the concepts. And then we have, after that layer, we have the computational units like wrapping feature generation modules and deep learning modules, and then name them and connect these two basically symbolic layer that we had in the data modeling and knowledge representation to this sub-symbolic layer of deep architectures. After that, we have this constraints-based training that we can use different types of algorithms and apply the logical expressions as soft or hard constraints during the training, or use them for the inference time only even. To just show the context, integration of domain knowledge is old idea used in probabilistic programming languages. Declarative knowledge representation, old idea used in probabilistic logical and statistical relational learning framework. Deep learning and logic probability, there are recent frameworks related to that. However, DomiKnowS has some new properties. It uses only Python methods and functions, no additional input scripts or languages. It's not bounded to any specific formalism. It's designed for integration. And also it has the two explicit symbolic and sub-symbolic sides. The data modeling here is explicitly designed and in a modular way addressed because we are dealing with structured data, and reading sensory data, raw data into the structure is kind of addressed here explicitly. The rest of this talk, please see Hossein describing the entity mention relation extraction programmed in DomiKnowS.
Hello everyone, I'm Hossein, and in the rest of this tutorial, I will walk you through how to program in DomiKnowS with the toy task of conal dataset for name, entity, and relationship extraction. So as for the first step, which is data modeling, DomiKnowS relies on a graph-based structure to declare the problem specification. The graph is basically formed with a set of concepts, relationships, and properties. Let's consider the conal task. For base concepts, we need to define word, phrase, sentence, and pair. And as a relationship between these concepts, we have to say that sentence contains phrase, which means sentence is a parent of phrases. And also, this defines that the pair is a relationship between two arguments of the same type phrase. We also have some derived concepts, which are basically the outputs like concepts or the latent concepts of our networks. Like here, we say entity is a type of phrase, people is a type of entity, organization is a type of entity, workforce is a type of pair, located is a type of pair. Next thing that we have to do, we have to bring in the knowledge that we have. And to represent that knowledge, we can either use, if we have already stored it as an ontology based on the OWL, we can either just import it, or we can use the Python-based specific language that we have for expressing the first order logical constraints. So this is the equivalent of saying like people is a concept of type word, and then it's disjoint with organization. Or you can use this line, the function that says disjoint people and organization. And for this like rule here, there's a more complicated rule that says if the type of pair is worked for, then its first argument should be of type people. Its second argument should be of type organization. You see that we have like logical operations, the graph paths, and the variable definitions. Next is that you actually want to solve the problem, so we have to define the computational units. Assuming that you already have these computational units outside of the framework, we have designed a lot of like wrappers called sensors in our framework that you can bring all those functionalities in without needing to rewrite them or do a lot of extra efforts. So at its simplest version, the sensor basically receives your function or neural model and connects it to the graph. And then the connection is made by introducing new properties of concepts that you have defined. So essentially, each sensor receives a set of input properties, applies a specific function that you have defined for it, and then stores the output into a different set of properties. Let's see some examples. So for instance, if you want to read the text of the phrases from your data set, then we have provided a reader sensor that you can do that with. That's the reader sensor is a wrapper. Or if you want to actually use the spacey word-to-vec representation function that you already have written outside, you can just connect it to the wrapper called functional sensor here. So here, this function is already written. This text is already like read from the data, and this is passed as an input to this function, and the output is generated is stored in this other property, W2V, and the same graph. Or if you want to use your PyTorch modules, we have a different wrapper called module learner. And you see that the module pass to it is exactly what we would use in PyTorch, and we have said this is the input, and this is where we want to store the outputs. Next, after you have your solution and you have your model, you want to actually execute it. In order to execute things, we have something called program that you have to define what is the constraint integration method that you want, what are the loss functions, the points of supervision for a network, what is the metric trackers, and the inference algorithms that you want to use. And it's just as easy as defining them in a specific instance of this program class. If you want to use different integration methods, we can easily just use different classes of program that we provide. So for instance, if you want to do a soft integration method with Primal-Dual, you can call Primal-Dual program. Or if you want to run a hard inference-masked integration, you can call IML program. You can also define different inference on top of your decisions. You can simply just use argmax or do an ILP optimization just by passing that into infer type of these programs. For testing, for actual training and testing, you can also call program that train and test with their respective parameters. This also makes it easy to define different training paradigms based on the same like declaration. So if you want to do an end-to-end training, for instance, based on the entities and a relationship at the same time, you would just pass both phrase and pair to the POI of the same program. Or if you want to do a pipeline first for, like for instance, entities, then relations, you define two programs, first phrase, train it, and then pair and train it. Or if you want to first pre-train the entities and then fine-tune the entities with the relations, you train the program based on the POI phrase, and then you define another program for phrase and pair altogether and train it again. The framework also provides you with cool visualization tools at 2 points. You can visualize the graph as you can see here, or you can visualize your instances of the graphs after we have filled them with data. So as you can see, like this is one phrase and the different properties that we have defined for it on one of the samples. In order to make it easy for you to start working with DomiKnowS, we have provided a set of examples for conal, WAQA, CFAR, image classification, graph coloring, email spam, sentiment analysis, and we are working toward adding more and more examples. We want to thank all of our collaborators in DomiKnowS for DomiKnowS in HLR Lab, and also thank you for watching this video. Please come into our in-person or virtual sessions or find us at the following emails.